Okay, so here we are. We're going to take a look at Ohm's Law today. In your textbook, page 258, should look something like this. Pearson, Saskatchewan Science 9 textbook is where some of these pages are coming from here. The textbook we're using, page 258. Okay, so Ohm's Law. So we've talked a little bit about electricity, about basic simple circuits, right? Series, circuits in series, circuits in parallel. We did a little bit of an activity there where you tried some different arrangements, series and parallels with different bulbs and things like that, made some observations. We're going to talk about Ohm's Law. Now, in science, there's a lot of sort of concepts that we need to learn and just learning about a situation, but we also need to do some calculations to be exact sometimes. And in science, the math and calculations is actually a large part of science, okay? So that's, this is sort of, now we're going to take a look at an equation called Ohm's Law that relates voltage and resistance and current. So these are things that we've talked about. So let's go over this in a little more detail. But first, let's take a look at the guy here that the Ohm's Law is named after. And his name is, it's not George, doesn't have an E on the end, it's Georg. Georg Ohm. Georg Ohm. Ohm, that's him right there. Okay? So the circuit boards and computers work because of the relationships between voltage, current, and resistance. These relationships have been understood for about 200 years because of the work of Georg Ohm. So this is a motherboard. So we've got some wires and some capacitors and resistors, and there's current flowing through each of these, but different amounts of current, different amounts of resistance in different parts help to save the electronics and help them to work properly. So Georg Simon Ohm grew up in Germany in the early 1800s. In high school, he studied physics, chemistry, math, and philosophy. He spent most of his free time playing billiards, which is like pool, ice skating, and dancing with his friends. All right. No one imagined that one day he would be a famous name in science. After graduation, Ohm went to a private school in Switzerland to teach, where he taught mathematics and dreamed of studying with great mathematicians at an important university. Ohm continued to study mathematics. One day, he was asked to instruct in the electricity labs. This was a turning point in Ohm's life. Fascinated by electricity, he immersed himself in the study of the electronics of voltage, current, and resistance. The next page, which I do not have up on the screen, I'll continue reading the last little part. Ohm's passion and commitment to his studies led to a deep understanding of how these different electrical concepts were related. Much of what he discovered, you have already learned in this unit. He stated these discoveries in what we today call Ohm's Law. So Ohm's Law established the relationship, as I mentioned, between voltage, that's the V. So if we look, where was it here? Right here. So Ohm's Law. The V is voltage. There's a relationship between voltage, current, which is symbolized by the letter I, and resistance, that's the letter R. And so if we have current multiplied by resistance, we would get voltage. And from this equation, we can also determine how to calculate current, or we can learn how to calculate resistance. So let's see, whoops. Okay, so we've got Ohm's Law is voltage. And of course, when we talk about batteries, right, the volts is the big V. Voltage equals current times resistance. So remember, the voltage is V, and it's sort of like the power behind the electrons, right? The power, the pushing power behind the electrons to push them through a circuit. Current is symbolized by the letter I, and current is the actual kind of amount of electrons that are flowing through the circuit. So there's the push, here's the electron flow, and then the resistance, and you can use a little X. In math in high school, a lot of times we use a little dot to represent the times, okay, a little dot in the middle. Not a period on the bottom or a dot up top, but a dot in the middle. That means multiply. And resistance is capital R. And this resistance would be sort of like any load that the electrons are supposed to pass through. So we've got the push, okay, we've got the actual flow, and we've got the load resistance, okay? So if you are pushing something and it's really hard to push, that means there's a lot of resistance. So you wouldn't be able to push it very fast. So you could have a lot of voltage, But if you have a lot of resistance, you don't have a lot of flow. If you have a big push and you're pushing something really, really tiny and light, you could actually push that thing very fast and very easily, and that would be a large flow. Question?
Why is current represented with I instead of a C?
Well, because why is current I instead of C? I guess there's a lot of different words in science that have their own symbols. So C is used for a lot of other things. Capital C, coulombs, little c, speed of light. I mean, the list goes on and on and on. So there's a lot of C's already. There would probably be a better reason for I, which I do not have at my disposal right now. It could be something to do with the Latin. It could be something to do with, I don't know. I'll look that up there. Or you could look that up. That would be a good idea. You should look that up. What relationship does I have with current, and why did they choose that? Other than C is taken by some other things. Okay, so V equals I times R. Now, from this, okay, so obviously we could find voltage if we're given current and resistance, but I want to show you a little something. I don't know if you guys have seen anything like this before, but I want you to draw in your notes here, I want you to draw a little, a triangle. Well, maybe not little. It's got to be big enough so you can put some stuff inside the triangle. Draw a triangle, and I want you to draw a T in the middle, like this. A T in the middle. Okay? Now, this is something that if you have an equation here with three quantities, okay, and they're related like this, you can draw this little triangle, and this will help you to identify how you can manipulate the equation, okay? So we have V equals IR, okay? I times R. So I'm going to put V up here, up at the top, and I'm going to put I on the left in the bottom and R on the right in the bottom. Okay? Now, V equals IR. If I want to solve for V, in this case, I look over to this little triangle, and what I do is I cover up the V that I'm trying to find, okay? I cover it up. And what I'm left with is I next to R, right beside each other. And when they're next to each other, you multiply. So V, if you cover it up, you know that you multiply current times resistance. And of course, that's Ohm's Law there. Now, if I want to find out what R is, mathematically over here, I would divide, and you can tell me if this looks familiar or not, I would divide both sides by I, and I would get R equals, because the I's are divided out, V divided by I. Okay? That's how you can determine R. Or you can write it like this, R on the left is V divided by I. So how would I use this little triangle here to show that? Well, I would cover up R. Here I'm covering up R. And look at V is on top of I. So I go voltage divided by current. And that's how you can use this little triangle to help you remember this. So V equals IR is the first one. And R equals V over I would be the second sort of version of Ohm's Law here, okay? It's just a manipulated version. And the third one, if we divide both sides by R to get I by itself, current equals what? V over R. So let's try this. I'm going to cover up I now, and you see how I have V on top of R, V divided by R. So this little triangle is helpful when you have an equation with three quantities, and you just cover up whatever you're trying to find, and that's a good way you can remember if you're multiplying or dividing. So if you did R divided by V, that's no good. That's not going to get you I. It's got to be V divided by R, so R has to be on the bottom, and so on. Okay? So any questions about that? What about units here? What about units? Let's see. So they talk about units here. Well, I guess it's kind of throughout the textbook. Let's go to this next page here. So here's V equals IR, okay? If you want to find out the voltage of the battery, and you knew the current, and you knew the resistance that it was going through, you just multiply those, and that gives you voltage. So what are the units here? Okay, here's a little chart that we just kind of worked through. Okay, so current is measured in amperes, right? Current is measured in amperes. Resistance is measured in ohms. Have we talked about ohms yet?
Yes.
I don't think we've talked about it. You've probably seen it though.
Yeah.
This little omega here, okay, that's the symbol for ohms. Okay, that's a uppercase omega? Yeah. It's the last letter in the Greek alphabet, ohms. And that is the symbol for resistance. So 30 ohms would be the resistance that some kind of just straight resistor would provide, or a load would provide, of some kind of resistance. And then finally, the volts is, of course, just V for voltage, okay? Voltage for V. All right, so here's an example problem. You don't have to write this down. It's in your textbook. Let's just walk through it, okay? If you have a current of 4 amps, and it's flowing through a 40 ohm resistor in a circuit, calculate the voltage. Well, it's pretty easy because we know that V, the voltage, equals I times R. I is going to be in amps, not any other unit, not milliamps, is amps. And the resistance has to be in ohms. So guess what? We go 4 amps times 40 ohms gives us 160 volts. 160 volts. Okay? Now, remember, our batteries that we used were 1.5 volts. Not a lot of power, pushing power. 160 volts is quite a lot of pushing power. So if you have 4 amps of flow and you're going through 40 amps, you need a lot of voltage. Okay? So these numbers would be higher than your typical little thing that you have just a AA battery for, right? The amps would be pretty low, the resistance would be pretty low to give a pretty low voltage. All right. Now we could find out for, for example, if we just, let's just do this as an example. So let's say I want to find out, what kind of resistance I would actually be able to use if I had volts were 1.5 volts. Okay, that's your battery, and we had a current of, let's say, 2 amps. Okay, 2 amps for current. What would the resistance be then? So we have one little, let's say a AA battery, okay, one little AA battery, and you have a resistance of, a current of 2 amps that needs to flow through your electronics, whatever it is. So what's the resistance going to be then? And we could find out R. So what is R? Well, you cover up R here, and you got V divided by I. So R equals 1.5 divided by 2. The resistance would have to be 0.75 ohms. So that's pretty low compared to that last question we did, right?
Mr. MathWell, is amps?
Okay, so the typical resistance of a 100-watt light bulb is 9.5 ohms. So if we took a look at that, and this little calculation that we just did for our 1.5 volts, it would be able to go 2 amps through 0.75 ohms. That's pretty small. I'm not sure about this current yet, but this light bulb needs 9.5 ohms, okay? So if it's plugged into the wall, that's 120 volts coming out of the electricity in the wall, 120. And so Ohm's law tells us that the bulb would draw about 12.5 amps. So notice we have a voltage here, and we have a resistance. We could calculate the electronic current, okay? And there's a little bit more about here, but yeah, that's how they're related, Ohm's law, okay? So a common light bulb would give a resistance of about 9.5 volts. All right, so 12.5 amps, that would give us 9.5 ohms, sorry, we would need 120 volts. Okay. Let's get back to our book here.
Can I flick off the lights later so the front ones?
What?
Can I flick off the lights?
Yeah.
This is nervous.
Okay, we talked a little bit about this yesterday in class 2, and this is on page 262 of your textbook. Short circuits. Okay, so we did a little activity yesterday, and you guys were to create a short circuit, and you would have had some observations about what happens in this short circuit. So let's just explain what a short circuit is. So here we have a battery, or it looks like 2 battery cells connected here. And then as we go along the circuit here, well, let's go this way maybe. As we go through here, the electrons have a choice to go this path or this path. Now, this path is going to provide a lot of resistance. This path has no load on it. So this is called a short circuit because the electricity can sense that, hey, you know what? There's a lot of, I have to fight pretty hard to get through these guys here. This one's a pretty easy path. So the electrons are most of them are going to just do this little loop because it's nice and easy. The electrons can, in a sense, feel the resistance. So current can flow more easily through the wire path than through the light bulbs. This creates a short circuit, which could be dangerous. So you could get really, this could get really hot because all the electrons are going to go through here, and sort of thing. So look what happens in this little cartoon situation, right? If you have this truck here that's run into a power pole and the electrical wire is somehow broken and it's fallen onto the truck, well, instead of the electricity going through these lines and powering all these homes and businesses, the electricity says, hey guys, we got a little shortcut to the ground here. Let's all take this. And so they get through here, and this could be a real dangerous short circuit situation where the electricity all wants to get to the ground through this vehicle. And if this ever happens, you just stay tight. Don't try and get out of your car. Don't touch things. Don't move around too much. You just hang tight because there's electricity flowing, and you don't want to kind of get in the way of that.
Unless you go on the top of the car.
No, you can't go on top of the car. No, you don't go on top of the car. You just sit tight. Chances of this happening, though, you probably get struck by lightning before this will happen to you. However, if it does, you know what to do.
Would it stop the car?
The car would be stopped already. Yeah, it would. Yeah, it would fry the electronics in the car probably. Yeah. All right. So let's see. Without a complete path, the driver might be safe here. I think it said, okay, the driver is safe as long as he stays inside the truck. Okay, don't move. Don't try and get out. Don't touch all the metal components. Okay. Moving on from there. What about, what's the next thing I have here? Oh, yeah, this double page. That's good. Okay, fuses and circuit breakers. We know a little bit about that. Let me talk about the importance of fuses and circuit breakers. Electronics can only handle a certain volume of electrons flowing through them, right? A certain sort of current. And so you would have something called a fuse that would be in the path where there are electronics that the electricity is flowing through. So why would you put these? Well, a fuse is only built to allow a certain amount of current to flow through it. And if there's more current than what it's designed to hold, then the fuse will blow, or the fuse will basically create a open circuit, and so electricity stops flowing. So circuit breakers, here is what an electrical panel in your house might look like. You have all these big black circuit breakers, and maybe you've seen this. Usually there's a big gray metal electrical box in your basement, and if you open up that little door, you would see these kind of circuit breaker panels. How many of you have ever been in your house and all of a sudden the power goes out, but the power doesn't go out in the whole house, it just goes out, you're using a heater or someone's using the microwave, okay? So what happens here is electricity is flowing through different lines and through different circuit breakers. And if there's too much current that is being drawn through the wires, so for example, this happens in our house when I've got the heater on in the basement, my son has his little space heater on in his room, and we're watching TV and we've got the whatever. So if all this stuff is going and it happens to be on the same circuit, well, the demand of the electronics is is demanding too much current, and there's a danger of it either frying the lines that the electricity is going through or the electronics themselves. It's too much for the circuit. And so what'll happen is this will literally flip. It'll go click, and then it'll cut all electricity in that circuit. So if that happens, it's like, oh, the TV just went off, the heater just went off, we flipped a breaker. Okay, that's what you would say, or you would hear. You flip a breaker. Or this circuit breaker went from the closed position, allowing electricity to flow through it, to open, stopping all the electricity from flowing. Yes?
Why does my garage and
Yeah, why would you have more than one in your house, maybe? You'll have one maybe in your garage, like you said, okay, because there's different electrical outlets and there's lots of lights and different things, and there's electricity that has to feed the garage and the related things in the garage, and that would have a separate set of breakers. Then you might have one in your basement that has all the plugs and the lights and the fridge and the stove and all that stuff would be in it, and you might even have a third one in your basement as well for things like a hot tub or things like that that has its own dedicated breaker box and stuff like that. So if you have a big home and lots of things going through there, you will have lots of these circuit breakers to protect your electronics and to protect the safety of the house, so that things don't get too hot or melt your wiring and stuff like that. So fuses come, I'll take your question in a minute. Fuses come in different sizes and shapes, okay? They look something like this. Sometimes fuses would look like, in the vehicle, okay, in your car, if you look at your fuse box, you would have something that looks like this, where you have like metal, two metal prongs like this, okay? And then inside you would see that there would be some kind of like, metal piece like that. And this would be like, let's say 15A, okay? Something like that. So what that means, right? What that means is that this fuse, okay, so there'll be electricity coming through here, in through here, and it goes through this tiny little wire, this little metal piece, and it goes out to your electronics, let's say your radio or something in your car, all right? And if there's a spike in electricity that could destroy your radio or could wreck your electronic components, the big wave of electricity that maybe might spike through would boom, it would split this right here, and this would break, the amp would blow, the fuse would blow, and your fuse would then it would look like this. It would literally be kind of broken. It would be melted there because there's too much current that's been blowing through there. So you would pull it out, find out what's wrong, and replace it with the new one. Okay? So this is why also you have like some of the power bars have like, what's the word I'm thinking of?
The little switch?
Yeah, the little switches, but they have like a power surge protector, right? So they kind of have something like this built in. Okay? Any other questions? Sure. Okay, so we'll just talk a little bit about this 3-prong plug here. So when you plug things into the wall, you'll notice that your wall outlets have the three holes, right? You have the kind of the vertical holes, and then you have this big round hole. And a 1 prong of the 3-prong plug carries the current to the load. Another prong returns the current to the source. And then the third is a ground. So it directs the current to the ground in case of a short circuit. So this is like a little bit of a protection too, that if there's a short circuit, that if there's a lot of electricity coming through, it'll just kind of go to the ground and protect your stuff. Okay? All right. Let's see. Let's do a couple questions before we get to our review here. So let's write some ohm questions down here. So copy and complete this chart. We're going to get some practice using our formula for Ohm's Law. So remember, these are the 3 versions, right, of Ohm's Law. And so if you have to find I, you take the voltage and simply divide it by the resistance. So go ahead and, you can use a calculator for sure. Yeah, go ahead and take some time here to fill in this chart, and then we'll see how you did. All right, so let's just double check these. So I want to find I, so I need to go voltage. So that would be, let's see, I'm going to clear this. That would be 0.5, okay, divided by 50. Divided by 50. That's going to be a pretty small number. 0.01 is what that is. So let's see. 0.01, and that's going to be amps. So let's make sure we have our units in there as well. Okay, if you had 0.01 amps, you did this exactly correctly. All right, so I'm solving for V, so I need to multiply 20 times 100. Hopefully you don't need your calculator for this one. When you multiply by 10 or 100 or 1,000, all you do is add zeros or move the decimal place to the right, however many zeros you have. So this is going to be 20 plus 2 more zeros, so that's going to be 2,000. 2,000 volts. That's a lot. That's a lot of current, okay? That's a lot of current, and this is a lot of resistance. So you're going to need a lot of volts. Okay, finally, question?
Would that be like for like a car loader?
Yeah, that'd be for some bigger machine maybe, you bet. Yeah, absolutely. Yeah, some big industrial machine maybe. Okay, so R, let's do V divided by I. So that's going to be 6, And it's 6.0, so you can put 6.0. You probably don't have to, though, in your calculator, divided by 4.0. And you can just use 4 if it's 0.0. That's fine. So if we do 6 divided by 4, is that right? So let's see, R is V over I. V over I, okay. So that's going to be 1.5 ohms. Very good. 1.5 ohms. I like drawing the ohm symbol there, the omega. I like that. The alpha and the omega. Huh? Beginning and the end. Okay. All right, so that's Ohm's law. A relationship between voltage, current, and resistance. It seems like a pretty simple thing, doesn't it?
Yeah.
But I mean, I guess, you know, how you come up with that, right? Lots of little experimentation, lots of measurements and things like that. Sometimes it's a simple formula in science, and sometimes it's not a simple formula at all.
So what did you do is the calculator?
Okay, grade 9s, that's the end of the lesson here. What I'm going to do is I'm going to hand out a question sheet that each of you are going to work through. Please look through your text, page 258 to 264. For the answers, the answers will be in the notes and the textbook here, okay? And I'll have that available for you here and on the website there.
Mr. Maxwell, when do you want these